And hello, my wonderful AP Physics 1 students. This is your preparatory video for day 3. We're going to review velocity. We're also going to introduce the complex idea of acceleration. Again, you should have your notebooks ready. You can be writing down some things for me. You're also going to be taking some time and pausing the video to think about some questions I'll be asking you. Let's begin. Quick review. As you might remember, velocity is the displacement in a period of time, whereas displacement is your change in position. So we see that velocity v here is the change, delta, of position in time in meters per second. And just like displacement, it also has two parts. Velocity has a direction, which you can call positive, negative, north, south, east, west, angles to the east, towards Chipotle, whatever, some kind of direction. And it's also got an amount, 35, 22. But that word amount I don't like. So let's replace it with the word magnitude. From now on, magnitude will mean amount. So displacement and velocity both need to have a direction and a magnitude to make them displacement and velocity. Just one doesn't cut it. So let's see a scenario and talk about velocity. We're about to describe the difference between an overall, which is we called average again, and an individual velocity. So take a moment and take that pen or pencil in your hand and toss it straight up and let it come back down your hand. Yep, if you missed it, please pick it up. Alright, so in this case, the average or overall displacement is 0 because it started and ended at the same position. Your hand theoretically shouldn't have moved. If your hand moved up an inch or so, then the displacement would not be 0 because it ended at a different height than it started. So what would the overall velocity here be? Well, if the displacement is 0, the overall, aka the average velocity, which you defined as the position change over the time, aka displacement over time, will also be 0. But in reality, we know it's not the case. It's obviously moving. It starts off going really fast, and as it goes up and up and up, it starts slowing, stopped, and then it starts getting faster and faster as it comes back down. So even though the average, or the overall velocity is 0, that's not really the velocity at every moment of its journey. So if you don't mind, let's call the time from here to the top as t1. You may want to put a little bracket here and write t1 next to it. And the time down is called t2. Since they're symmetrical, we can say they're equal, but don't worry about that right now. Let's also say that the ball goes from your hand to some height h in t1, and then it goes from h back down to your hand in t2. Starts off here, goes up to height h, comes back from h down to here. So on the way up, the velocity for that first time segment, v1 is a time in t1, will be positive h over t1. Positive h is the displacement, t1 is the time. On the way down, the velocity is going to be negative h over t2. Negative h because displacement is final minus initial. Let's say your final height is 0. Your starting height is h. 0 minus h gives you negative h. And notice this. Since these are kind of average or overall velocities for the time period, we use a little v with a line over it. So v with a line kind of means average or overall for that time period. So line with just the v is 0 because that's the overall part. Velocity 1, average, is this because it's just the average for the first half, average for the second half. Both velocities have equal magnitudes, but they have different directions. H is the same without positive, negative. T is the same. So they have the same amount, same magnitude, but they have totally different directions. And that makes a big difference. So, in summary, we can actually break the throw into more and more time periods we can call t. T1, T2, T3. Each has its own individual velocity. At the most extreme part of it, every moment of time in that throw has its own velocity amount. Let's call that the instantaneous velocity. It's the velocity for an almost minuscule amount of time. So in that throw, there's almost an infinite number of instantaneous velocities. So let's have a basic equation for instantaneous velocity. But you're not going to write this equation down. You're going to try to understand it instead. Because this equation is not very useful until you're in your third year of college or so. Actually, second year of college. And here it is. The velocity, notice there's no line above it, so it's not an average or an overall for a time period. It's really the velocity at one point at time. Is the limit as the change in time approaches zero of your change in position over change in time, which is also called dx over dt. Now at this point you might be like, what the fudge? So let me make it easier for you. Okay. What this statement is saying is, as the time between the first and second point of motion almost becomes zero. So instead of looking at, time t1 where it starts in your hand, and then the pencil or pen or ball ends at the top, we're looking at from 0.00000 seconds to like 0.00001 second. So the time difference is incredibly tiny. So then there's not much motion difference as well. It's very, very tiny. As that happens, this becomes super small, and the change becomes super small as well. So by limiting the time to a very small time period, it's almost the time at an instant. That idea is called a derivative. So this is just a way of looking at almost instant amounts of time, because the longer you look time-wise, the more you get an average or a muddled amount of knowledge. So in other words, tossing the thing up and coming back down, instead of looking at long time periods like from this ball to this ball, which there's a large change in its velocity, it starts off here and it gets slower, 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 we're looking at literally like from this ball to just a fraction of a moment beyond it, or from here to here, and so forth and so forth. There are three special instantaneous velocities that we care about. The first is the initial velocity, v naught. This is the velocity at the start of some defined motion. The next one will be the final velocity, usually called vf, or just v at times. And then sometimes the velocity, the max height and distances are also pretty important. Now, big note of caution here. V naught, vf, and these kind of things, they're all defined differently in different situations. So, from the boy's point of view, the entire throw can be considered a time period. V naught is right here, vf is right here. Or we could say, for the second half of the ball's throw, v naught is up here, vf is down here. Or looking from this ball to this ball's time period, this position right here has got some initial velocity, this has got some final velocity. Initial and final are just defined based on the time period you're looking at. And in physics, it becomes really important to sometimes just look at small chunks of time in between certain motions. So now for the last part, let's look at acceleration. It's the idea of how quickly you change your speed. The symbol is A. It's in meters per second squared, which from your packet you know, it's a length over a time squared. And just like velocity and displacement, it also has a magnitude and it has a direction. So at this point, I'm going to ask you one or two questions. I want you to pause the video. I'm going to give you a chance to do it before you answer it. So let's consider a person who's got acceleration of positive 2 meters per second squared. In 1 second, how much velocity would they have gained? What about 2 seconds? Pause, get ready to answer. All right. So if they gain 2 meters per second squared, that means that every second they gain 2 meters per second. So in 1 second, they gained 2 meters per second. In 2 seconds, they gained another 2, which is a total of 4 meters per second. So here's a question to you. Have they gotten faster? Pause, get ready to answer yes or no with an explanation. And of course, the answer is we cannot tell. We cannot tell because imagine the person was running backwards at first, which is why the little positive here is make the huge difference. If they were going backwards at -6 meters per second, after 1 second, they gained +2. So they went from -6 to -4. but they're still going backwards because their velocity is negative. After another second, so 2 seconds, they went from -6 to -4 to -2. So they're still going backwards. And they're slowing down backwards in this case. The only way you could say they're going faster is if you somehow knew that either they started at rest or that they were already moving in the positive direction. If you don't know that, the statement cannot be made. And with that, you are ready to rock and roll. I'm going to teach you a lot more. Have yourself a good day.